Okay, can you see a PowerPoint here? All right, away we go. I'm going to start my timer here. So it's a pleasure to be here. Thanks for the introduction. I'm Milo Koretsky, and I recently moved to Tufts University, and this bridge here represents a position. I'm a bridge professor, which means I have a half appointment in engineering and a half appointment in education. And my job, among others, is to bridge these two worlds. So today I want to talk about one aspect of the work we do, which is the promotion of active concept-based learning pedagogies. And I'd like to start with just two problems that your students may see. But the first one is a problem in which they're given a circuit with a given voltage and a bunch of parallel and series resistances. And they're asked to determine the current through one of the resistors, R3. So if you just want to take a few seconds and think about how you might solve this problem. Okay, the second question is asks about the same diagram, but says when the value of R6 increases, what happens to the current through R3? Does it increase, decrease, or stay the same? And the question here is, what's common about these and how are they different? Okay, so if you want to put in the question and answer in chat any ideas about how they're common and how they're different. But the theme of those is that this first question is what I'll call a computational problem. And here's another computational problem. This is a flow through a valve, where in this case you have steam going from 8 megapascals to atmospheric pressure. And this problem, how as an instructor I would expect students to answer it is to write the first law, eliminate the appropriate terms, and this ends up being an isenthalpic process. So H in equals H out, or H1 equals H2. And from that, students can solve for the solution. And when they do that, they do pretty good at this. So in one case, 53 out of 61 students in a class get it. Then if we go and ask, well, what about a conceptual question? So here's a question very similar. It's the same valve, but now instead of steam, we have an ideal gas. And they're not asked to calculate anything. We just want to know, does the temperature decrease, increase, stay the same, or you can't answer? And if we look at how students respond to, of course, because it's isenthalpic, the enthalpies are the same. And for an ideal gas, the enthalpy depends only on temperature. The correct answer is that the temperatures are equal. But if you look at the responses, only 8 students were able to answer this. And to compound that, these were the same students who answered the previous question, and the homework was actually sitting on the instructor's desk. So the homework were stacked on the desk when this was answered. So students are able to answer the procedural question, but not the conceptual question. Okay, so what's going on here? Well, one common way that's in culture to teaching is what I call a procedural approach, which is that students learn by example. And in the case of thermodynamics, they might be given some properties and shown steps and asked to find another property. Then for homework, they practice that. And for an exam, we might flip it, and instead of giving them T, we give them P, and they go through this and find T. They do well. Students think we've learned. Professor thinks I've taught. But they're just learning to follow patterns. This is what I'll call a conceptual approach, which is within a topic you identify concepts. And you might show